All right, everybody, here's part two of this problem. This is where things get a little bit weirder. Not anything that we haven't seen before, technically, but it might not have been something you've seen in a while. So, just to recap, if you need it, we're looking for the time it takes for this tank pretty much to drain until it reaches about this level. So, we got a bunch of work over here. And finally, what we've got is an equation for our Q in terms of h, and also a relationship between the changing height and the changing time, right? So we're going to set these two equal to each other. dH over dt. So you're kind of looking at this and you might be thinking, what the heck am I going to do with this? But the fun part is that this is going to be part calculus problem, right? This is the I forget the name of them, but it's like the differential equations. Yeah. So this is like an elementary differential equation that we're gonna have to do, but really it's just a little bit of calculus, because what we do is we move the dt over, and then we move everything else over with the dh, and so what we get is that the dt is equal to negative 500 over 0.000863 times square root of h plus 3, or divided by square root of h plus 3. And what we're going to do is we're going to integrate, right, to get rid of these differentials. So for time, we start at time 0 and we go to some time t, and then we start at some h1 and then we go to another h2, right? So this integral is easy enough. This just integrates out to t. On this side, we get something a little bit different. 863. Because we're going to start our first height, our original height is 25, and then our ending height is 5. So we're going to integrate from 25 to 5 the dh over square root of h plus 3. So if you remember your integrals, this will move out here pretty quick. So t will negative 500 over 0.000863. And then when we integrate this, we get 2 times the square root of h plus 3. H plus 30, sorry. That should be plus 30 all the way up. Got lost in sauce. Yeah, plus 30, right? All right, so h plus 30. And then 25 to 5. If you don't remember the connection from here to here, I suggest you find there's like online integral, like if you search integral calculator, there's one that'll do this for you and then walk you through step by step. Anywho, so let's see, because this is, you know what, I'll just explain it right here. Might as well. All right, so integral of dh times h plus 30 to the negative 1/2. So to integrate backwards, you just have to, so you add 1, and then you divide by whatever that value is. So it'll be h plus 30 to the positive 1/2 divided by 1/2. So the way that works out is just 2 times the square root of h plus 30. Yeah. So that's that little integral right there. And then we don't put a plus c because we have boundaries. Anyway, so now if you remember how these things work, multiply that 2 over, so it's negative 1,000 over 0.000863 multiplied by, then you plug this 5 in, so we get square root of 35 minus the square root of plug 25 in for h, and we get minus square root of 55. So this will give us a wildly large number, but that's going to be in seconds, right? Because we multiplied, because everything that we've been working in so far has been in terms of like meters, and then the gravity we put in was 9.8 meters per second squared. So I didn't want to track the dimensions all the way down, but what you'll get is this number. And since it's so large, you can pretty well assume that's going to be in seconds. So we're going to chomp that down into a little bit of a more manageable number. And if you do the conversion, you should get 483 hours. Right, divided by 3,600 seconds per hour. So this is a kind of a wild problem. Yeah, when I saw it and started working out, I realized it was going to be, this is probably going to be more intense than what you would actually see on an exam. But I figured it was worth seeing just because this is like a fairly practical problem. It's like how fast is this thing going to stop draining? And then, yeah. I think most problems that you'll run into will probably end right about here, right? Because you'll solve for a friction factor, and then you get something in terms of H or in terms of Q, and then you solve for it. In this case, we had to go with a little bit of calculus, but I think that's not, it's not unreasonable to, to figure that we might have to do that. So if you see this problem and you're kind of bamboozled by just kind of how weird it is, I wouldn't be too worried about it. Definitely, I would say out of the three problems 1 and 2 are very representative of something you might see on this third exam. This problem 3, good practice, maybe a little bit overboard for review, but that's better than not reviewing enough. All right, so I will also be going over the multiple choice problems because there were some WebEx issues earlier today, and so yeah, I will do that in the next video, so watch that one too.